forces that usually we cannot see it. Sorry. Hope that this video will play. Yep. So what we got it here is magnetic fluid. So very dense suspension of the stable magnetic particles in usually it's organic solvent. And on the upper side, we got magnet. Below, it's magnetic fluid, and the magnetic fluid is floating towards the magnetic field. And all those spikes, those are basically the representation of magnetic forces, the magnetic field. Because we all know, as a kids, and also now, we usually played with the magnets, so the materials that stick together when they are in one orientation, but when we change the orientation, so flip one side, so one magnet to the opposite side, they repel. So what is this strange force, invisible force? So this asked questions already asked himself Albert Einstein, and this was as they reported, the first scientific question from him when he was a little. So magnetic forces, we cannot see it directly, but indirectly we can visualize it with such nice magnetic fluids, which are not good just for the presentation, but as I will present you later, they are also applicable. So magnetic materials, we can find it basically almost everywhere. It's the most common material in the world, probably where we are sitting now in our offices or lecture rooms. All around us, we will find few kilos of magnets around us. So you can find it, of course, in the cars, in our vehicles, in coils, so speakers. There are natural magnetic materials in our phones, computers, of course, fridge magnets, so almost everywhere. So how everything starts? The magnetism or magnetic materials were already known in antiquity. So the first known material was magnetite, Fe3O4, so iron oxide, which naturally attract iron. Back then, they did not know what this force is that binds two rocks together, but the same rock did not bind with another, so they probably found the explanation in the gods. But later, through the history, we knew that this is magnetism. So magnet, because it was already known in antiquity, means magnetis litus, so magnetic stone. In novel age, so by the 20th century, magnetic materials were already known in China, because they were using compass for navigation. So Earth magnetic pole attract magnetic needle in a compass, and Alexander Neckham was the first European who described compass and his role in the navigation and bring this instrument in Europe. In 1819, there was first connection between electricity and magnetic field. So this connection described Hans Christian Ørsted. He described this with the use of magnetic needle under the influence of the electric field. Basically, he created an electromagnet, and the magnetic field aligned with the magnetic force. In 1820, Andrea Maria Ampere discovered first magnetic field that travel in closed path, and that this is connected with the radius of path. So how strength of the magnetic field decreases or increases. Then Jean-Baptiste Biot and Felix Savard describe how a magnetic field act in the wire, so how the wire carry the electric current. This is described in the Biot-Savart law. After that, Marie Faraday describes time-varying magnetic flux through the wire loops, that this induces voltage. And in the beginning of 20th century, James Clerk Maxwell combined electric energy, magnetism, optics on the field of electromagnetism, and described everything this in the Maxwell equation, which are now like basics equation for this electromagnetism. Of course, this Maxwell equation was so important that also Einstein uses in the relativity theory. And now in the 21st century, electromagnetism and magnetism generally is still ongoing research field. We cannot imagine our life without the magnets. Since 21st century, we developed the fundamental theories, so quantum electrodynamic theory, standard model, meter model, and so on the basis of all the discoveries from the future. So application of the magnetic materials rely on the response of this material to the magnetic field. And the magnetic field in the atom originates from the charged particles movement. So we know three types of movement of charged particles movement in the atom. So we got oscillation of protons in nucleus. This got really small influence on the response to the magnetic field, and so we ignore it. But more important are circulation of electrons in orbits and rotation of electrons around its own axis, so the spins. So the whole magnetic moment of the material depends on the structure of materials, how the atoms are arranged in the crystal structure, how it's the circulation of the electrons in orbits and its spins, and all of this. So all of this is described in some vector of sum of all of those circulation of movements. So magnetic moment of all magnetic moment of all electrons cancel each other. So this happen in the atoms with paired valent electrons. We don't have the net magnetic moment, and we got diamagnetic material. If the cancellation is only partial, we got some net magnetic moment. This happens in the atoms with unpaired valent electrons, and we got magnetic material, or so with the magnetic atoms. And here we observe, first of all, paramagnetism, and with that also antiferromagnetism, ferrimagnetism. So basically, all the materials are magnetic, even those that we called non-magnetic. I will explain you later. But only ferro and ferrimagnetic materials are generally used. So those materials we use in industry, in everyday life, and so on. So here below, we got the scheme how the magnetic materials are basically divided into dia and paramagnetic materials and ferro, ferri, antiferromagnetic materials. So magnetism and magnetic materials and how they respond to the magnetic field, they can be described in few equations. So when magnetic material is exposed to the external magnetic field, individual atomic moments in the material aligned toward the external magnetic field and give the overall response. And this response to external magnetic field is described with magnetic energy, which is defined by the magnetic field, moment of material, and the magnetic constant, so permeability of the free space. Then we can also describe the flux of magnetic lines. So the density of those magnetic lines in some material, this is called flux. We can see that is connected to the electron, to the magnetic energy, and then also to the external magnetic field and magnetic response, so magnetism of the material. The magnetism is then is described as a magnetic moment per volume. So because the magnetic properties of some material are measured as direct response to the external magnetic field, we need to know it, or it's better to describe this response as the ratio between the magnetism, so magnetic moment per volume of material, and external magnetic field. But if we want to have the, so this is called the susceptibility. And if we need to know the flux compared to the magnetic field, we describe this with permeability. So as I told you before, we classify the magnetic materials according to their bulk susceptibility. So susceptibility is magnetic moment, so magnetism, how it acts in some magnetic field. So we got then paramagnetic, diamagnetic, ferro, anti, and ferrimagnetic materials. Those blue ones are classified according to the spin arrangement. Dia and paramagnetic are classified according to the susceptibility. As you will see it later, also ferri and so this got negative susceptibility, positive susceptibility, and also those got positive susceptibility, but we got some small differences in it. So dia and paramagnetic materials, as you can see it here. So diamagnetic materials are composed of atoms with no net magnetic moment. So the electron moments cancel each other out. Magnetic response is opposite to the applied magnetic field. We got so-called negative magnetism, small and negative susceptibility, and such response to the magnetic field express inert gases, many metals, most non-metals, and organic compounds. If you remember, I was talking that all the materials are basically magnetic, that they've got some magnetic response to it, even non-magnetic, because we can still measure, let's say, non-magnetism like this. So on the other side, we got the paramagnetic materials. They are composed of atoms with unpaired valent electrons. Here we got some net magnetic moment, so vector of magnetic moment pointing toward a certain direction. Electron spins and atoms are randomly oriented, and this gives us the net magnetic moment. When such material is exposed to the magnetic field, moments tend to align parallel with the direction of an applied field, and we can measure such response. So with positive susceptibility, the response is in the same direction as the field is pointing. Such properties express liquid oxygen, rare earth salts, ferromagnetic materials above UV temperature. and so on. Then we got like a special group of magnetic materials that are not that they've got similar response to the paramagnetic materials. So when they are exposed to the external magnetic field, spins and moments align towards the direction of this field, but we got some differences, which we will not go today, so because it's really in deep physics behind this. So such materials are ferro, ferri, and antiferromagnetic materials. So as we can see it here, we can represent them by this direction of the spins. So those arrows are spins. So ferromagnetic material below QD temperature, they are spontaneously magnetic, but above QD temperature, they become paramagnetic. So this QD temperature is the temperature when the spontaneously magnetic material become non-magnetic. So it's not magnetic when we remove external magnetic field. So here, when the field is not present, so external magnetic field is not present, spins are still orientated parallel to each other. And we got some net magnetic moment and strong response. So when the field is, so when such material is exposed to the magnetic field, they exhibit strong response to this field. They've got large permeability and susceptibility. Opposite to this, we got antiferromagnetic materials, where the spins of neighboring atoms are oriented antiparallel. They cancel the magnetic moment is zero, so we got the cancellation of it, and such materials don't exhibit spontaneous magnetism. Under the external magnetic field, they act like ferromagnetic materials, so all the spins are orientated to the into the direction of magnetic field, and we get such image. Special case are ferrimagnetic materials. Those are special classes of antiferromagnetism. Neighboring moments are antiparallel, but magnitude different. So as we can see, we got antiparallel orientation, but one group of moments, so strength of one group prevails over another, and such materials exhibit spontaneous magnetization. So material is divided into two different sublattices, which one prevail over the other. And they've got spontaneous magnetization below nil temperature, but become again paramagnetic above this nil temperature. This nil temperature is analog to the QD temperature. So above this temperature, the spontaneous magnetization is vanished, and we got the material which is as paramagnetic. Ferrimagnetism is expressing the materials where between the two metallic ions is positioned also the oxygen. So we get, for instance, in iron oxide, iron, oxygen, iron, and we get this oxygen bridge. So everywhere where we have the magnetic materials, the oxides, we got the ferrimagnetic materials. But so in this case, this was the perfect representation, for instance. So each spin, so each arrow represents each atom. But of course, in the nature, it's not like this. So the material is not magnetized uniformly, because the material is consisted of magnetic domains. So those are areas of the ferromagnet that are magnetized to the saturation, so to the maximum value of magnetization, but the magnetization of domain vary from one domain to the another. So as we can see it here, this happened in the bulk material. We got different domains where inside each domain the spins are oriented in one direction. So we got some net magnetization in this direction, but on the other, we got the net magnetic moment pointing to on the other way. So magnetic domains are separated by the domain wall, which can move under the influence of the external magnetic field. And this influence can be described or visualized in the hysteresis loop, which I will present a little bit later. So here below, we got, for instance, if you imagine, in the middle is the domain wall. And the magnetic field is pointing towards here, so up. And in the domain wall, the spins start to flip towards the direction of the external magnetic field. And then this flipping is it's happening, starts to happen also on the other domain when the spins are oriented on the other direction of the magnetic field. And with this mechanism, we can reach the total saturation of material, so where the spins of all the domains are pointing in the same direction of the magnetic field. But the magnetic domains, so the uniformity of magnetization inside one material, depend on the size of the material. So for instance, we got multi-domain material in the bulk. So a large, so when the diameter increases, numbers of domains increases. Then we can, then we reach some diameter where we reach also the maximum numbers of those domains. And with decreasing, so when we decrease the size of the particles, we also reduce the number of domains, and in some case, under certain diameter, we came into the single domain regime. So from this bulk material, when we decrease the size, we get to the single domain regime. And here we can represent, for instance, one magnetic moment as one material. So as we decrease the particle size, we can also come to this so-called super paramagnetism, which is really some sort of paramagnetism. But I will describe you a little bit later. So as I said, the response of the external magnetic field, so also the movement of those domains and net magnetic moment inside different domains, can be represented by hysteresis loop. Hysteresis loops are loops are representation of response to the magnetic field only for ferromagnetic materials. We cannot find it with paramagnetic materials because we got just a line, but not this loop. So here we have to know a few terms. At the beginning, so at 0, we got randomly oriented domains, and the net magnetic moment can be 0. So we got demagnetized material. When we increase the magnetic external magnetic field, the domain spins inside the material starts to point towards the direction of the external magnetic field. We also see that the domain walls start to decrease, and at some point, all the magnetic moments in the material, so all the domains, magnetic moments in the domain are pointing in the same direction. So all the spins, everything is pointing in the same direction. So we reach the maximum magnetization, so saturation magnetization of the material. And the spins are oriented in the into the direction of the external field. Then we flip a external magnetic field, and we are going through this line. And those spins start to rotate, and when the field is zero, the point, so magnetization at the point where the external magnetization is zero, we call it remanent magnetization. So value of the magnetization without the influence of the magnetic field. Then we start to flip the magnetic field in the negative side so that we demagnetize magnetic material, so that the field in a material is zero. This is corrosivity. So magnetic field strength needed for the demagnetization of the material, and magnetization, so M is zero. Then the whole story repeated, but on the negative side. So with increasing the magnetic field into the negative side, we again saturate the material. So all the spins are in all the domains are oriented in the same direction. And then back to the remanent magnetization and corrosivity and so on. And we can drive around this hysteresis loop. One important value that the strength of the ferromagnetic materials is described is BH max. So the maximum energy product of the material, this is the figure of merit for strength of magnets. If, for instance, somebody asks you how strong this magnet is, you have to give him this number, so BH max. And also according to this, so area in the second quadrant, the magnetic materials are we choose magnetic materials for different magnetic applications. We also classify then this pair of ferromagnetic materials according to the shape of the hysteresis loop. So we know soft magnetic, hard magnetic materials, and super paramagnetic materials. So soft magnetic materials are those that are easy to magnetize. So we need small magnetic field that we reach saturation magnetization. And their hysteresis loop is really narrow, but quite high. They've got also, so because small magnetic field is needed for magnetization, we need also small magnetic field for demagnetization, and this corrosivity is quite low. On the other hand, we got hard magnetic materials, or we call it permanent magnets. Those are magnetic materials that we generally use it in our industry. So for such materials to saturate, we need large magnetic fields, so large corrosivity. They've got quite moderate saturation magnetization and really large BH max, so energy product. Compared to the soft magnetic materials, you can see it here, saturation magnetization is smaller, but corrosivity is bigger, and also energy, high energy product is bigger. Special case which depend on the size. So we found this only in the nano regions, so nanoparticles, and below the certain level, which is called superparamagnetic limits, are superparamagnetic materials. As we can see it here from this hysteresis loop, when we don't have the external magnetic field, they are not spontaneously magnetized. When we switch on external magnetic field, they act like ferromagnetic materials. When we switch off, they are paramagnetic materials. So such materials don't have the corrosivity or remanent magnetization. And this case is, as I said, it depending on the size effect. So nanoparticles. Of course, all the materials do not have the same superparamagnetic limit. It's differ from material to material, but usually it's around from 50 nanometers to 20 nanometers or then below. Another really nice representation of the magnetic field beside the magnetic fluids or hysteresis loops is magnetic field visualization on the microscope, on the transmission electron microscope. Those are special setups where we can then, with help of the computers and programs, we can visualize our magnetic field. Here we got the representation of barium hexafluoride. So it's some kind of iron oxide with barium inside. The special thing about barium hexafluoride is that it's got shape and magnetic anisotropy. So this means we got hexagonal material, but it's hard magnetic, so hard axis of magnetization. It's pointing in this direction, so crossing the plates. And because of that, the magnetic field is different in this direction than this direction. And here we can also see it here. When the particle is analyzed from above, we can see that the lines are going around and they're concentrating somewhere in the middle. So this means that they're going from the up down. But when we image it from side, when we image the smaller dimension, we can see it that those magnetic lines are really passing the platelets. So the visualization of the magnetic moments, it's not limited only to the ferromagnetic materials, so those that got spontaneous magnetization, but also on the antiferromagnetic materials. This is the recent article from November 2021. And here we got alpha iron oxide. And here we can see by the Lorentz microscopy. So Lorentz microscopy is the microscopy for visualizing the magnetic moments on the TEM. And by help with a computer, of course, we can then determine in which direction magnetic moment is pointing. So we help with this polar chart and with some simulations, and then we can see if the simulation is the same as our measurements. So visualization of the magnetic fields, so with a magnet or any other tool. For instance, we can use also X or D, so pole figures, so how the some magnet is orientated. It's very important, especially for the industry, because we really want to use such, for instance, ceramic magnets, which is some disc that is used in the proper direction, where the field is the strongest, not in the direction where the field is the lowest, because all of the materials don't have the uniform magnetization all around, so in all the axes. So besides ferromagnetic materials, we can also somehow couple them, so mix ferromagnetic or even antiferromagnetic materials together, and we get the composite materials. So those can be called also novel magnets, because we join, so we couple two different magnetic properties, so two different magnetic materials together, and the result is somehow sum of those materials. So the first such case is indirect exchange coupling, which appear between the layers consisted of ferromagnetic transitional metal material, which is separated by non-magnetic layer, as it is here presented. So cobalt iron, which is then separated by non-magnetic ruthenium. So by thickness of the thickness of the phases and thickness of the non-magnetic spacer gives us if we got antiferromagnetic material or ferromagnetic material. So you can see it here that depending on the spacer thickness, we can have here in this case antiferromagnetic materials, so those black dots, and in some case the ferromagnetic materials. And this is very important. For instance, if you got antiferromagnetic material for DC current detectors, or ferromagnetic material for soft magnetic magnets. The other type which we quite often use, or probably those who use computers, is the exchange bias coupling. This appears between ferro and ferromagnetic material and antiferromagnetic material, so combination of those two. It is meant for overcoming the superparamagnetism. So as I said it, superparamagnetic materials don't have coercivity or remanent magnetization, so no spontaneous magnetization. So we somehow push the spontaneous magnetization into the material. This is very important, especially in the storage media industry. As we can see it here, we got some representation of storage media. So we got some random non-aligned magnetic particles, and then our read-write head is going along this disk, and with the magnetic moment produced with the coil, we can write or read our information, which is stored with zeros and ones, and zeros and one corresponds to the alignment of the spins in the magnetic nanoparticles. But we always want to have smaller, faster, better computers, mobiles, so we have to also use smaller particles. And as I said it, with decreasing the particle size, we also reach the superparamagnetic limit. At the superparamagnetic limit, thermal energy prevail over the magnetic moment, and such particles don't exhibit spontaneous magnetization. So this means when they are not exposed to the magnetic field, they again randomly orientate. And as if you imagine, if we got such particles inside, we write, so orientate the particles when the coil is removed. So our read-to-write head magnet is removed, the particles start to orientate randomly, and we lose our information. So what's happening with the exchange bias? So when we couple ferromagnetic material with antiferromagnetic. This happens between neo and QD temperature. So between neo and QD temperature, so for instance, in room temperature, we got such image. So ferromagnetic material, we got spontaneous magnetization. In antiferromagnetic, we don't have spontaneous magnetization, and magnetic moment is zero. Then the material is saturated, so to the highest magnetization, and field cooled, so below new temperature. And we got the orientation of the ferromagnetic material and antiferromagnetic material. Then we start to decrease the magnetic field. Ferromagnetic spin starts to flip towards the external field, but antiferromagnetic materials are the same. But what happened on the at the border of the both materials is that ferromagnetic materials are pinned by the antiferromagnetic materials, and then we need higher corrosivity field that we flip our ferromagnetic spins, and because of that, the whole hysteresis loop is shifted. And of course, then we somehow push our corrosivity and remanent magnetization into our material, and we can use smaller nanoparticles that usually in room temperature exhibit super paramagnetism, but here we got magnetic with some material with spontaneous magnetization. The third case is the exchange coupling materials, so composites. These occur between the soft and hard magnetic materials. As I said, soft magnetic materials are those with low corrosivity, quite modest remanent magnetization, and high saturation magnetization, compared to the hard magnetic, which got moderate or small saturation magnetization and quite high corrosivity. So when we put together those two materials, we get the hysteresis loop, so magnetic properties that result from the sum of both properties. So this is the ideal case. And with this, we can also increase or even somehow choose or change also the BH max. So so term for merit of how strong the material is. But the problem is that the materials have to be really coupled. So in close contact, but the close contact is not enough. They have to be even the materials epitaxially grown together, because if they are not, we get such kink and we lose the magnetic properties basically of both materials. So that for exchange couple to be really effective, the first one, the first one were group from Spain, that they reported that really for exchange coupled materials, the materials have to be epitaxially grown together. Otherwise, we got just dipolar coupling, and we don't get really broad hysteresis loop, but with this kink. So at the Ojo Stefan Institute a few years ago, I was also, this was basically my PhD thesis. We somehow built or synthesized the composite nanoparticles, where we got barium hexafluoride nanoparticles as a core, and then epitaxially growth maghemite, so iron oxide layers on it. And this is basically the representation how the material should be, so the exchange coupling will work out. Of course, with the thickness of the layer, the size of the particles, we can then also the shift change this corrosivity or remanent magnetization and saturation magnetization. So this was one overview about what are the magnetic materials, how we describe them, generally how we classify them, but where we can find those magnets. For instance, as I said it, hard magnetic materials are those that are massively used. So those are permanent magnets. Here you can see the share of the permanent magnets in the market. So neodymium iron bore, ferrite magnets are then on samari cobalt, and now the newest are all-nickel magnets. They're usually in motors, generators, then storage drives, transportation, energy production, storage. This is so this part is now growing because a lot of magnets is needed for instance, in the batteries for wind turbines, so on. And then we got some small shares also in the other area. So this was by percentage, but by the mass, we can see that we use mostly ferrite-based magnets. Then we got neodymium iron bore, and then a small share as samari cobalt and all-nickel magnets. So why is this? Because the application of magnetic materials in the industry based on the energy product. So ferrite magnets, we can reach up to the certain level. So it's the moderate. So up to the certain level of energy product. But then we got the gap of materials that we cannot for now reach those values. And above this value, we got neodymium iron bore materials with really high energy products. So this gap between energy product of neodymium iron bore and ferrite magnets, it's now, for now we are filling with this samari cobalt and all-nickel magnets, but also with modern magnets, or with those composite materials. Also, the problems of usage of those permanent magnets is that, for instance, neodymium iron bore and samari cobalt magnets, they have those rare earth magnets. And as we all know, the geopolitical situation in our world, the most of it, those rare earth elements got the Chinese. So this is also the problem, for, especially for Europe or America. So they are depending on the market. So from the Chinese to produce and give them those metals. As a representation, as I said, it permanent magnets are all around us. For instance, in the car, especially now in the electric car, we got from 5 to 10 kilos of permanent magnets just in one car. If we subtract all the chassis, the tires and everything, this is quite a big number. We can find it in sensor, ignition coils, everywhere we got some electricity, so electric motors, sensor, even electric brake, starter generator, valves, seatbelt sensor, and so on. The modern cars are even got those magnetic fluid brakes that because when we apply a brake, we somehow ignite, as I said, the magnetic field. So by pushing the brake, we increase the strength of the magnetic field in some container in between its magnetic fluid, and by applying different magnetic field into this magnetic fluid, we we change the density of the magnetic fluid, and so we also press on the brakes and we stop the car. The same principle can be used for shock absorbers. So by changing the viscosity, also how the shock absorbers react to the bombs around us. So those are hard magnetic materials, for instance. They can, so as I said, they are used nowadays in wind turbines, for instance, in all like electric motors, sensors, and so on. Everywhere we find sensors, electric motors, we will find hard magnetic materials. On the other hand, also soft magnetic materials are quite common nowadays. Usually they are used in some as a nanoparticles, or even, let's say, microparticles, micrometer particles. The big area, the big field is biomedicine. Really known, and let's say quite time now, we know magnetic fluid hypothermia. So it's the alternative for chemotherapy. Here we locally inject magnetic particles, of course, coated with some molecules that attach to the cancer. Then we apply the magnetic field. Those particles are locally heat up, and they locally basically burn the cancer. So as I said, it can be used as a individual method or together with chemotherapy. And then we all know magnetic resonance imaging. Usually for imaging, we need some contrast, and this contrast contain colloidal particles of some magnetic material. Then we need it for bacteria detection. On the magnetic particles, we can bind different molecules that bind on the bacteria, and then with, for instance, fluorescence microscopy, we can detect them. Then we can immobilize enzymes. We label cells, separate cells, or even then target. We got target drug delivery. This is the same principle as in magnetic fluid hypothermia, where we got magnetic particles coated with our targeting molecules, and then with the magnetic field, we somehow guide our magnetic particles towards the certain part of our body where we want to deliver this drug. So in everyday life, we know it. We came across with soft magnetic materials, those QR codes, barcodes. Even for safety reasons, they are in our cache. Very interesting is, for instance, in those fishing rods, we got those magnetic fluids. So when the magnets with magnetic fluid came together, the magnetic fluids interact, and it acts like some kind of prevention for water to come inside this mechanism where we got our fishing rod. So those were, let's say, usual way of using hard and soft magnetic materials, but I will present a little bit about some research propositions or some, let's say, unusual ways that are currently are not still in massive use, but I hope they will come eventually. First of all, as I said, I present to you later before barium hexafluoride nanoparticles. They are very interesting because of its shape, anisotropy, and also magnetic anisotropy. So this means that hard field, hard direction of the magnetization is pointing only on the one direction. So it's not uniformly placed. So for instance, when we expose such plate nanoparticle, magnetic nanoparticles into the external magnetic field, this magnetic field of the particle will try to align with our magnet. And if we are doing this in some circular motion, this particle will flip around and we will have some small magnetic rotor. And this can be applied for cell destruction, for instance. So magnetomechanical excitation of nanoparticle so that we break some liposomes, some, for instance, cells, and so on. So this can be additional method how to cure the cancer. This is the already published paper where they successfully break the membranes of phospholipids with such magnetic nanoparticles. As we can see it, or even in 6 seconds, the phospholipid is completely destroyed. The second one, which can be used, for instance, for drug delivery, it's magnetic assembly of iron oxide nanoparticles. I forgot to tell that iron oxide nanoparticles are only one that are approved by FDA for medical use. So those are the only material that can be put really officially into the body, and it's already used. So such clusters of super paramagnetic nanoparticles coated with silica layer can be formed into such nanochains under the applied magnetic field, and depending on the field strength, we get a different length of those nanochains. Additionally, we can also dissolve this iron oxide with the concentrated hydrochloric acid, and we got hollow silica spheres. And then we can put our drug or something else inside, and then we got the targeting the liver, for instance. Then the iron oxide nanoparticles are already used many years in pharmacy or for a lack of iron in blood treatment. So anyone who came across with anemia, say this is lack of iron, usually the doctors gave you all pills or intravenosis, so IV, directly into your veins. They pump you with iron liquid. So the last one, what I want you to see where we can use also iron oxide or magnetic particles, which is a little bit more strange, is with the wine sparkling production. For instance, so here on the images, we can see those big balls is yeast, and those small particles are iron oxide particles. absorbed on the yeast. So especially for sparkling wine production, the most known is champagne. The production is so that the bottles, for instance, you can see they are orientated with neck down, and this yeast is extracted. So they rotate the bottle. After 1 year or even longer, they freeze the neck and then extract the yeast out. So this can last for years. So for really good sparkling wine, but with this magnetic separation, we can faster this procedure. For instance, if this is wine with the yeast, we just expose this wine to the magnetic field. Magnetic particles and the yeast, so yeast with magnetic particles will be attracted to the magnetic field, and we can extract easily, nicely the yeast, and we got good sparkling wine. So this was all from my side for today. Here is the if someone wants to know a little bit more about the magnetism, those are the most common books, especially Coolity, and then the authority of the magnetism for the Cowie with his books and articles. So thank you for your attention, and if someone got any questions.
Yeah, thank you, Dr. Belek. We have queries from participant side, so I would like to unmute Mubashir. Hello,
Yeah.
Mubashir? Yeah, you can. Mubashir, are you there? Hello? Hello, Mubashir?
I can maybe answer this on the chat. I saw.
Sure.
Yeah, this so paramagnetic materials also has zero corrosivity. So why it's special about the superparamagnetism? Superparamagnetism always occur as a function of size. So always occur in the nanoparticles, while paramagnetic materials are also bulk materials. The superparamagnetism you will not find in the bulk materials. So this is the differences.
I guess he has posted more than one query, so should I read other one?
Uh, I just see
Earlier,
one question, nothing else.
so earlier he asked that oxygen has pair electrons. Then
Yeah.
what is the reason for its paramagnetism?
So oxygen,
Has
why it's yeah, this is in the liquid oxygen. So here is also the case of the temperature.
okay. Another question he asked that if antiferromagnetic materials have no net magnetic moment, then what is the importance of Neel temperature?
Uh, what is important of the Neel temperature in antiferromagnetic materials?
Yes. He want to
Uh, sorry, this I don't know the answer about this.
know. The question is the Neel temperature works where this ferromagnetic to paramagnetic transition is there. But if the material
So
is only
in ferromagnetic material, so ferro, so without oxygen inside, we got Curie temperature. So below this Curie temperature, which is so it's quite okay, it can be at room temperature or quite high. Uh, so below Curie temperature, the ferromagnetic material exhibits spontaneous magnetization. So it's got net magnetic moment. Then on the other hand, we got ferrimagnetic materials. So we got nil temperature, which is analog to the Curie temperature. And it's act the same. Below it, ferrimagnetic materials, so as iron oxide got um, spontaneous magnetization. Above it, they've got, so they act as paramagnetic materials. So no spontaneous magnetization.
So I hope Mubashir you are satisfied with the answer. You have received the answer of your question. So there is one more question from Mubashir. Actually, Mubashir is working on materials for magnetic applications. So he's quite interested in or find it very much suitable in his application. So next question is paramagnetic materials also has zero corrosivity. What is special about supermagnetism?
It's the same answer as before. Super paramagnetism is always acting when we got small particles. So nanoparticles, one domain particles. So single domain. For instance, for iron oxide is around 10, barium hexafluoride is around 50 nanometers. Below this uh, size, we get super paramagnetic materials, while paramagnetic materials are in bulk. So paramagnetic materials can be super paramagnetic, but not vice versa.
Okay, and so next question is
So it's always this is the nano size effect, super paramagnetism.
okay. And next question is from Chintak Parashar. He wants to know that magnetic material strength. What happens to magnetic material strength when these materials are immersed in a fluid?
So fluid test, for instance, that's water or some. For instance, if we just put it in water, it's nothing happened. We just get the suspension.
Let
Uh,
me
so,
unmute him. He
so,
will ask directly. Yeah, Chintak, I have unmuted you. You can ask your question. Chintak, are you there? Hello, Chintak. So I think there is some internet issue with Chintak.
so
So
for as I understand, if you got magnetic material and you put it in some liquid, for instance, water, nothing happened. The magnetic material will be still magnetic. Um, Usually, all the nanoparticles should be in suspension in water or other solvent. As I present you in this magnetic separation for wine production, those are basically magnetic materials, magnetic particles in water. If you will dry it, you will get the same hysteresis loop as if you will, for instance, measure the magnetic properties of magnetic fluid. But okay, in magnetic fluid, you have to somehow freeze this fluid so you don't get the rotation of the particles inside them. The
so
magnetic properties are the same.
so actually his question was that he want to know the relation in magnetic change in magnetic property with time when we immerse it into a fluid in relation with biological application.
Ah, uh, Here we have to know how the biological media act with magnetic particles, if it will dissolve it or not. If they will be dissolved, of course, because the particles get size reduced, so also the magnetic properties will change. Um, and if nothing happened, the properties will be the same. Of course, the important is how we measure what we measure. For instance, if we usually hysteresis loop saturation magnetization is expressed by emus per gram. So uh, responds to the gram. If we got just magnetic particles, we will, for instance, measure 10 emus per gram. If we put it in some biological media where we got also the cells and everything and dry this, we will have mass which is consistent from mass of the particles and mass of the uh, cells. And of course, the emus per gram will be lower, but still, if you will calculate it back, how many percentage of the magnetic properties you've got it inside is the same. Of course, you have to take into the account that the strength, so how the strength of the external magnetic power can be reduced, but due to all the other stuff in your medium.
Okay,
I
so I
hope
hope
that uh,
Chintak is satisfied with the answer he wrote in the chat box. So next question same from Mubashir. He is asking in magnetic multilayer like in spin value, how to control magnetization of individual layer relative to each other.
uh, so usually those layers are built up from so one by one, and of course, if we got already built up some um, multi-layer, we cannot then modify each layer by itself because then we got coupling between the spins and so on. So when we build up such layers, first there are some simulations, and then layer by layer we build the multi-layer, and then with the thickness of the layer and the, the dimensions, we somehow manage to control the magnetization of individual layer. But of course, when we put two magnetic layers together, we will always get some sum of both, so some interactions.
Okay, I hope
Especially on the interfaces. If we got thick enough in the center of the layer, it will be as in the bulk, but in the on the interfaces, we will always get some interactions, so magnetization from the result of this.
okay, I hope Mubashir is satisfied with the answer. Thank you, Professor Blay. We have one more question from Sumit Kumar. He is asking that what is the difference between alpha iron oxide and beta iron oxide nanoparticle, and what changes the nature of semiconductor from N type to P type?
About the first, so alpha and beta, those are different uh, structural modification of iron oxide. They're all iron 3 oxides too, but they've got different uh, ratios between ratios between iron not sorry not ratio um, different um, uh, um, crystallography. So um, the atoms are in the material are put together in different way as on the, for instance, maghamite. So because of that, we got alpha iron oxide is hematite, which is usually it's not magnetic, and gamma is maghamite, which is magnetic, but both are Fa2O3. About the other I'm sorry, I don't know the answer for this. So from one to the another, I'm not so into this field.
Okay, no, sir. It's yeah. So I request if there is any query from the participant side, they can put it in chat box or they can raise at their hand to ask Dr. Blaze directly. We have enough time for query session. So yeah, Dr. Blaze, thank you for such a nice talk on magnetic materials. I hope there
Okay.
is no query from participant side. So we can move forward.
Thank you for your attention.
So participant, this is it for the day. Tomorrow we have two lectures from Professor Valence. He is going to deliver the lectures on heterogeneous photocatalysis and photocatalytic materials in morning session. After that, in evening session, we'll have an exam of 2 hours, which will comprises all the basic questions we have gone through during this course duration. Thank you for the joining.